Hello, everybody. My name is Keith, and I'm going to give you a brief introduction to footfall induced vibration, looking at why it's important, what we currently know, and how we can design with it in mind. The design of a building structure is linked to the overall design vision. Consequently, this often means longer spans are more common because spaces need to be open plan or flexible. At the same time, we generally want to optimize structural material usage for both economic and sustainability reasons. You might even need to minimize the overall structural floor depth for building services or to reduce the overall building height. The typical design approach has worked well for years, and it still does. It's normally governed by some design code and regulations. That usually means satisfying ultimate limit state criteria for safety and strength. And it also involves some serviceability check, normally focused on deflection or sometimes cracking. The overall focus is on a static system because we typically don't want buildings to move. Dynamic behavior is often considered separately or not at all. There are some old vibration assessment methods. They are quite simple, however, they make a lot of assumptions, so they tend to not be accurate. They can even overestimate and underestimate vibration response. Arguably, human activity is the primary reason why most buildings even exist. And to design for this, we normally idealize the intended activity to some static load. However, people move. Those activities often induce periodic forces, such as walking or running. So the reality is that there is some dynamic nature to human occupation. Now, let's visualize the situation. On one side, we have modern design trends that tend towards longer spans, potentially with relatively shallow depths. And generally speaking, we as engineers need to be more sustainable or economic with the materials that we specify. The typical design approach has worked well for decades. However, traditional methods for assessing dynamic behavior often lack the accuracy required for many structures today. These two factors together tend to produce structures that are more susceptible to footfall vibration. Most buildings meet strength and serviceability requirements, but that doesn't mean they will feel right. A large open plan floor can meet all the typical structural design requirements, but still have noticeable vibration problems when occupied. Footfall-induced vibration is a serviceability issue. Broadly speaking, we're looking at two categories. The first is occupant discomfort. This is where occupants might describe parts of the floor as bouncy or lively. What it essentially means is that the vibration is noticeable enough for them to make a comment or complaint. Our perception of vibration depends on what we are doing. Now, as designers, we can link this to an intended use of a space or room. So, for example, people in a gymnasium would notice vibration less than medical staff in an operating room. Floor vibration can also affect machine operation. This might include sensitive lab equipment, medical facilities, or high-precision manufacturing machinery. In each of these categories, excessive vibration means suboptimal usability. And, in the worst case, the floor might not even be fit for its intended purpose. So there are real consequences when vibration is excessive. If a building has been constructed, then a vibration problem is found. You could retrofit dampers or make structural changes. Both are significant work. It's expensive, disruptive, and not great for anybody's reputation. If occupants are complaining about vibration after construction, then it's really too late. You ideally want to solve this at the design stage, when it's quicker, cheaper, and there's less risk. The design stage is when you have the most freedom to explore and solve the problem. Remember, simplified rules and methods are often overly conservative and can occasionally underestimate vibration. The building industry as a whole is more aware of vibration. This is ultimately leading to higher specifications for vibration performance in some projects. So, what is the way forward? How can you reliably assess footfall vibration at the design stage without overly compromising material efficiency? Guidance is already available. The three main design methods are outlined in SCI P354, CCI P016, and AISC Design Guide 11. They all outline a method for assessing footfall-induced vibration, where the goal is to help engineers assess dynamic structural behavior against measurable comfort criteria, ultimately allowing you to make better design decisions. These three methods can be followed in SCIA Engineer. The first step is to create a model, and this is normally a single floor unless there is some interaction between multiple floor levels. Depending on the method and your judgment, you can alter material properties, support conditions, or member connections. After, you prepare the model for a modal analysis, and this means creating mass groups and combinations of mass. Keep in mind that for vibration, less mass is more conservative, so when creating mass combinations, you typically want the least feasible combination of mass. Next, you set up a footfall load case. Here, you set the main settings for the analysis. If you are familiar with SCIA already, this is very similar to a seismic analysis setup. After that's done, you can then define the extent of pedestrian movement. What you're defining is the location of where activity can occur. Finally, you run the analysis and review the results. At this point, you can make more informed and targeted design decisions. For example, adding extra members to critical areas or maybe additional mass. These types of changes will have the most significant effect on the vibration response. The prerequisites to perform footfall analysis are you need to have SCIA Engineer 26 installed. You also need the Professional Edition or higher. And within each project, you need to activate the modal and harmonic analysis module that can be found under the general module of dynamics. Let's just briefly introduce the main setup component, which is the footfall load case. This is very similar to setting up a seismic load case. It is possible to have multiple footfall load cases, and they do not interact with each other. For every footfall load case, you define the overall analysis settings. For example, you can control which design method or footfall coefficients will be used. We'll take a closer look at these in more detail later. It might seem strange we define footfall as a load case, but the reason why is so that we can define specific areas of pedestrian movement. You can use load objects to define these exposed locations or areas where activity can occur. Remember, these loads are not treated as static loads. They just define the areas exposed to pedestrian movement. These activity locations can be modeled using point loads, line loads, or defined by a 2D region, and they can all be found in the input panel. Similar to how static loads are defined, these dynamic areas will be assigned to the active load case. So we need to make sure a footfall load case is active. As an example, you can use a free surface load to define localized regions of pedestrian movement for a single footfall load case. Now let's take a quick look at how this can be done in SCIA Engineer. So we're just going to use a relatively simple model just to demonstrate how you can set up a footfall load case and run the analysis. And the first thing that we're going to do is just to make sure that the project settings are correct. Specifically, we want to make sure that we have the correct functionality, which is the dynamic functionality and ultimately the modal analysis. Now, for a real project, you might want to alter material properties or change restraint conditions or boundary conditions such as supports or member end connections. Whatever design guide that you follow will give you advice on what to do there. So moving on, we need to create a mass group. I only have self-weight in this model, so I'm just going to be creating a single mass group based on self-weight. But in a real project, I might have another one for other permanent load or the floor imposed load. Next, we need to create a combination of mass. This is relatively simple in this demonstration because I only have one mass group representing the self-mass of the model. In a real project, this would be the least credible mass combination. So probably the permanent load plus some percentage of the imposed load. The design guide will usually give you some guidance there what you can use. Just remember that you're looking for the least mass. Okay, now we've set up the mass group. We can go to the load cases and we're going to create a new load case. Let's call this Footfall 1. Just delete the description for now. Change the action type to variable, specification, the load type to dynamic, and the specification to footfall. You can use two different types of damping, which is Rayleigh damping or constant damping. Whichever you use, the zeta value or the damping ratio you would need to set. Typically for buildings, that zeta value is somewhere between 2.5 to 5%. This is going to be on a project by project basis. But for the demonstration, let's just use 3%. The next thing that we need to decide is whether we're going to use self-excitation or full excitation. So self-excitation gives you the response results at the same location or node as the excitation force, whereas full excitation gives you the response at all nodes regardless of the location of the excitation force. So let's just take self-excitation for now. Then we need to specify the footfall coefficients. So we're going to create some new ones. I'll just go with the standard naming. The first one we'll have is the SCI. And for every design method, there'll be an activity. So we can choose walking activity. And the source we can use directly from the design guide, or we can manually create our own coefficients. But I'm just going to take it directly from the design guide. And we can create multiple footfall coefficients. So for example, we can create another one for the concrete center. And likewise for the AISC. Let's just select the first one. And once you have one selected, we'll see which design method we're using and which activity. Now we can manually specify a frequency range by activating manual frequency input. This allows us to edit the minimum and maximum walking frequency. If we deactivate it, then we just use the values directly from the design method. An important point to remember, the minimum and maximum frequency apply to the first harmonic. Higher harmonics are automatically calculated as multiples of these frequencies. So for example, the second harmonic is 2 times the first frequency and the third is 3 times and so on. The frequency step defines how the frequency range is divided for the analysis. Smaller steps means more accuracy, but at the cost of computation time. Depending on the design method, the walker is defined by either mass or weight. I believe for the SCI it's mass. And then we also need to specify the length of the path. This value represents the length of the expected walking path. It could be the length of the structure, or it could be guided by the actual room plan. Essentially, it represents the distance a person walks during the excitation. Other design methods have similar parameters, but it could be the number of steps instead of an actual length. You have the option to apply a weighting curve. The human body is more sensitive to certain frequencies and directions. Weighting curves are a way of adjusting vibration values to better represent how these vibrations might be felt by a person. So these curves come from international standards, so you can opt to use one of them if you wish. Whichever design method you are following will give you more information. The combination method significantly influences the predicted response. The design method you're using will tell you which ones you can use. Within SCIA, you have 4 options. There's SRSS, or square root of the sum of squares. There's SRSS-RMS, which is the root mean square of the square root of the sum of squares. There's the sum of peaks, or SOP, and then there is the root mean square of the sum of peaks. The difference between these combinations are probably best described using a graph. So this graph represents our vibration response, which has varying peaks. The red or blue lines represent the various combination methods that you can have. More conservative methods, like sum of peaks, assume that all peak responses from individual steps occur simultaneously, resulting in higher estimated vibrations and a safer but potentially over-designed solution. Less conservative methods, like SRSS, consider the steps as uncorrelated events, leading to lower and more realistic estimates that might better reflect random footstep timing. Just remember, choosing the appropriate method is essential to comply with the selected design method. So you should always refer back to the design method that you're using. Now let's just return to the model. You have the option of limiting the mode shapes that can be combined. Once we activate this, we get this value here, the frequency upper bound. If we select this as 15 Hertz, what this means is that any mode shapes above this frequency just won't be considered. Finally, the last value that we should concentrate on is the combination of mass groups. We have to link the footfall load case back to a combination of mass groups. Lucky for us, there's only one. Okay, and now let's just return. We'll add a meaningful description here. Let's say that this is SCI P354 self excitation. Now that we have the footfall load case active, we now need to define where a pedestrian movement can occur. And we do this via loads. So we can find them in the input panel. And I'm going to use a free surface load for this. There is no value or intensity to this load. You can see that in its properties. All we're doing is defining an area. Let's take this area. So this area is where our walker is present. Now it is possible to create multiple footfall load cases. So I'm just going to take a copy of this one. with its selected entities. And I'm going to change the excitation method to full. For completeness, change the description. We could even create other footfall load cases, but this time we could even totally change the coefficients. So let's say we're going to use the CCIP design method. And we can change the excitation method again. Rename this correctly. And we can create as many footfall load cases as we want. At this point, we are pretty much ready to run the analysis. To do that, we can go to Calculate and run the analysis. Now, because I have quite a few footfall load cases present, especially when using the full excitation method, the calculation can take some time. So I've actually gone ahead and pre-prepared a model. So let's just switch to that one now. So the results have already been calculated here. I actually have more footfall load cases. So I have self and full excitation for each design method, including the AISC guide as well. You can find the footfall vibration results under the detailed dynamics results. You simply select the load case, the specific footfall load case that you want to look at, and normally we want to look at the response factor. And we can refresh, and this is our response factor. So remember, this particular load case is for self-excitation. So it's only giving me the response underneath the area that I defined earlier where the pedestrian could be. If I switch to footfall 2, this has full excitation. We'll see all of the response across the whole floor for this specific area of excitation. Okay, so this is the main difference between the self and full excitation. You can get very similar results for the CCIP design method. It will give you the same thing. And for the AISC, you don't have a response factor, but you do have a peak acceleration, which is displayed in very much a similar manner. So it's at this point now where we can make some design decisions. We can decide whether the response is satisfactory enough for the usage of the floor. And if it isn't, then we might consider making some structural changes to make it less susceptible. Let's take a look at a few other examples. This is just an RC slab with columns and shear walls. And we'll change this to the stick and node view. And the loads that we have in terms of footfall, we have used the CCIP design method for both self-excitation and full excitation. And they have two different boundaries of where pedestrian movement can occur. The results have already been calculated, and we can go back to the dynamic detailed results. And we can look at the first footfall load case for the response factor. And then we can look at the second footfall load case for the response factor. I remember that this one has a more localized area of excitation. Now, the response factor is built up of two components. You have a resonant component and a transient component. And one of these will typically dominate depending on the frequency of the structure. When we select overall, we actually see the greatest of either of the two. So if I go to resonant now, this is the resonant frequency, and this is the transient response factor. So we can see that transient is greater than the resonant response factor, and the overall is now the same as the transient response factor. Let's say you want to investigate a particular area. If you have a node there, so we've got a single node here, then we can select the current node, and perhaps we want to look at the acceleration in that area. And then this would be our acceleration in that particular point. Okay, let's go to another model. Let's look at a composite floor. This is a relatively straightforward composite floor with composite beams, so it's got composite decking. Let's turn off the volumes, and we're going to turn off the extent of the loading. We have 4 different footfall locations, so this time we've used the SCI and the CCIP design methods in here for both self and full excitation. Now, when you have a composite floor, there's a couple of properties that you do need to change. So first, let's select the composite decking. We need to change the element behavior to standard FEM. This now means that we can calculate the dynamic behavior of the composite decking itself. Likewise, we need to do the same thing for the composite beam. So if we look at one of the beam properties, now instead of the standard connection type that you might have used for just the regular EC4 design, when looking at the vibration of the floor, some of the design methods will allow you to actually offset the beam. So here we have a user-defined eccentricity, and the beams are now aligned to the bottom of the decking. Okay, so let's take a look at the results. Very much the same. If we go to the detailed dynamic results, and again, we can look at one of the load cases and look at maybe the response factor. You can see here that this is the response factor for self-excitation. If you go to full, we'll see it for the overall floor, but for where we defined the pedestrian movement before. Again, if we look at the response type, we can have a little bit more detail by looking at, say, a particular response type. So let's say the resonant. If we refresh, we can see that, yes, it is the resonant response factor that is dominating. Okay, and this is supported if we go to the eigenfrequencies. We can see the mode shapes have fairly low frequencies. So it makes sense that the response factor is resonant dominant. You can also use footfall vibration on CLT floors or structures. This is a very small CLT structure, and we can run the same level of output. And we can get some response factor, although this is quite an unrealistic structure. But it's just to demonstrate that you can run footfall analysis on virtually any material or any orthotropic plate. If we look at this CLT plate, we can see that it is an orthotropic 2D member. And if we look under its properties, we can see it is calculating the stiffness of this 2D member based on the lamina of the CLT. Let's finish with some key takeaways. Modern structures are increasingly susceptible to footfall-induced vibration. Footfall vibration is a serviceability issue. Requiring a footfall vibration analysis is becoming more common. As previously mentioned, design methods are already available, and performing a footfall analysis helps you make more confident and cost-effective decisions. So that's it for this webinar. Hopefully you have more insight about footfall-induced vibration, how it might affect your work, and how you can assess it. Thank you for watching, and see you next time.